Alrighty, y'all. I'm going to start this video by saying that it is my earnest recommendation that you do not watch this whole video at once. I don't know how long it's going to be, but I think it might be fairly long, like maybe about an hour. You already know how long because you can see. Don't watch an hour of chemistry video at a time. It's not, first of all, it's not worth it. It's not worth your time to spend an hour straight doing it. Also, it's not the best for your brain. You are much better off, like learning wise, to spread this out over a few days. So, with that disclaimer out of the way, let's get started. Alright, so we got our heating curve math practice problems. This is posted to Google Classroom, so you can take a look at all the questions on your own screen, and you can test them, practice the calculations yourself. Then if you get stuck, you can skip ahead to where I'm working that problem, and you can see what my process is. Alright, I'm going to start by drawing a heating curve and drawing a cooling curve as well. Let's do my cooling curve in blue, and I'll do my heating curve in red. So remember, our heating curve is made of 5 segments, and what's happening at each segment is, remember that we have our phase changes happening at plateaus, and then we have solid, liquid, and gas just increasing temperature at the other, during those slopey sections. For our cooling curve, it's going to be the same thing, but in reverse. So we go down, flat, down, flat, down. And again, our phase changes fall on our plateaus. This time, instead of melting and boiling, we are condensing and freezing. But still we have gas, and then liquid, and then solid. Alright, so those are our heating and cooling curves, and our all of these numbers are used for specific segments of those heating and cooling curves. So our heat of fusion, this is used if we are on the melt or freeze plateau. Heat of vaporization is used when we are at the boil or condense plateau. Specific heat of water, of course, is when we are in a liquid state and we're changing the temperature. Specific heat of ice when we're in the solid state and changing the temperature. And specific heat of water vapor is when we are in the gas state and changing the temperature. So now for each of these questions, I'm going to start by drawing the segment of the heating or cooling curve that describes the process described. That's funny. In the question, we'll number each segment and then label my steps to do my calculations. So let's just jump in. A chemist is heating a container of liquid water. How much heat is required to raise the temperature of 250 grams of liquid water from 25 Celsius to 75 Celsius? So I know that this is a heating curve rather than a cooling curve because I'm increasing my temperature from 25 to 75. I have no phase changes described here, so no plateaus. This is actually really simple. It's just going to be a one-step. So I don't need to label this with a 1, but you can if you want. So that's the only step that I'm going to calculate, is going 250 grams of liquid water from 25 to 75. Since I'm heating liquid water, I'm going to use my specific heat of water, which is 4.18 joules per gram degree Celsius. And remember what that means, that 4.18 joules is the number of joules that is required to heat 1 gram of water by 1 degree Celsius. But my question is not asking about 1 gram of water, heating it by 1 degree Celsius. It's asking us about 250 grams of water, increasing by, 25 to 75, so that's 50 degrees. All right, so that's going to be a whole heck of a lot more joules than 4.18, right? The question is how many times more joules? And you can see that in order to get from 1 times 1 to 250 times 50, we have to both multiply by 250 and 50. So if I do both of those in sequence, I will figure out what my scale factor is here. So 250 times 50 is 12,500. So that is my scale factor here. And you can think about that as multiplying by 250, then multiplying by 50 is multiplying by 12,500. So I'll use that same scale factor on the left side over here, times 12,500. It must take 12,500 times as much energy compared to 4.18 because I'm heating up 250 times as much water and I'm heating it by 50 times as many degrees. So then I'll take my calculator and I'll type 4.18 times 12,500. And I got 52,250 joules. And that's my answer. Since this is only a one-stepper, I don't have anything to add up, so I can just report that as my final answer, 52,250 joules. All right, moving on to question number 2. During a controlled experiment, a 50-gram sample of steam at 100 degrees Celsius is cooled and condensed into liquid water, which then cools to 0 degrees Celsius and freezes completely into ice. What is the total energy released in this process? So we know we're starting at 100 degrees Celsius, and we also know that we're starting as steam, and we're eventually going to turn into ice. So I know right away this is going to be a cooling curve. I need to start at 100 degrees Celsius and end up as ice. So if I start as steam, go to ice, that's 2 phase changes that are going to occur. So I know that there should be 2 plateaus. And in this question, I'm actually starting with a plateau because I'm already at 100 degrees, which I know is the boiling point of water. All right. So it doesn't have to change temperature at all before it starts condensing. Even though it does say cooled there, I think that just might be a mistake because we're already at the temperature that is necessary in order to condense. So we'll condense, and then once we turn into a liquid, we will cool down further, and we will keep on cooling down until we get to 0 degrees Celsius, at which point we will freeze into a solid. So this looks like it's going to be a 3-step. I'll label these 1, 2, and 3, and then of course we'll add all of our energy quantities at the end. All right, so let's do step 1 first. We are condensing steam. Condensing steam. So we are going to use our heat of vaporization here, and that is the 2257 number. Remember that this time, 2257 joules, this time we don't need to worry about any degrees Celsius here because we're changing phase. And since we're changing phase, the temperature is staying constant the whole time. So I don't need to put like 1 degree Celsius here or anything because it just doesn't matter, right? The temperature is not changing. We're good to just leave it like this. 2257 is 1 gram. But of course, in my question, I don't have 1 gram of steam, but rather 50. So I can say 50 grams of steam. How much energy is required to, or how much energy is released, rather, when you condense 50 grams of steam into water. So it's going to be obviously 50 times more energy than 2257. So I can just multiply those 2 numbers together and I'll get my answer. All right, so I got 112,850 joules of energy required for step 1. For step 2, let's think, what state of matter are we in? Are we in a solid, a liquid, or a gas? Well, we just condensed, right? So after condensing, we should all be liquid. So for my specific heat, I am going to use my 4.18 number again. Again, I know to use a specific heat rather than a heat of fusion or vaporization because my temperature is changing. Anytime my temperature changes, I'm going to be using specific heat. Anytime my temperature is plateauing, I'm going to use either my 334 or my 2257, right? Heat of fusion, heat of vaporization. All right, so step 2, we're going to, like I said, use the 4.18 number. And again, that is the number of joules that is released when 1 gram of water cools down by 1 degree Celsius. But of course, I don't have 1 gram of water, but what was it, 50? I have 50 grams of water. And how much am I cooling down by? Let's take another look at my question. another look at my heating curve. What is the temperature difference between here and here? Well, it looks like, since we are going from the boiling point all the way down to the freezing point or the melting point, I know that water condenses at 100, and I know that water freezes at 0. So it must be going all the way down from 100 to 0. So that is a temperature change of 100. I am changing my temperature by 100 degrees. So I'm going to release a lot more than 4.18 joules. I need to figure out what is the scale factor between that quantity and that quantity. Remember, we can think of this as multiplying by 50 and multiplying by 100, which is the same as multiplying by 5,000. So since that is the scale factor here, I can use the same scale factor on the other side. 4.18 times 5,000. And I'll get 20,900 joules as my answer for step number 2. Next, we have step number 3, and you can see we are at a temperature plateau, so that means we are going to have to use one of our phase change heats. Since we are freezing, we'll use the heat of fusion, which is 334 joules per gram. So here we go. Here's step number 3. 334 joules is the amount of energy that is released when 1 gram of water freezes into ice. Now, I don't have 1 gram, I have 50. So this is going to release 50 times more energy. So I'll take my 334, multiply it by 50, and I get 16,700 joules. 16,700. So to do step 1, it takes 112,850 joules. To do step 2, it takes 20,900 joules. And to do step 3, it takes 16,700 joules. We are being asked what is the total energy released in this process, so we should add all of those numbers together. I got 150,450. And of course, that's joules. There we go. All right, moving on to question number 3. A student is observing the melting process of a substance in lab. 125 gram sample of ice melts at 0 degrees Celsius. Calculate the energy required for this phase change. So we are melting, so that's going to be a heating curve. Melting is a phase change, and it doesn't look like the temperature is going to change at all because we're already at 0, so we just have a one-stepper here. All right, so we got 125 grams melting. Since I'm melting, I'm going to use my heat of fusion, which is my 334. My 334, what does that number mean? It is the number of joules that is required to melt 1 gram of ice. I don't got 1 gram of ice. How much do I have? 125 grams. So I'm going to need 125 times as much energy to melt that much ice compared to the smaller amount. Right? So 334 times 125. And I get 41,750 joules. So this is just a one-stepper. I'm done. All right, number 4. In a physics demonstration, an ice cube is heated. Calculate the total energy required to convert a 45-gram ice cube at -10 into liquid water at 50 degrees Celsius. All right, so heating curve first. I know it's a heating curve because we're melting ice into liquid water. And we're also raising the temperature, right, from -10 up to 50. So if we're starting at -10, that means that we are below the melting point, because the melting point of ice is 0. So before we can melt, we have to raise the temperature, and then we can melt. And then we have to raise the temperature again, because we're going from 0 up to 50, right? So those are my 3 segments. This is another 3-stepper. So I will label my steps as I go. Step 1, what do we have to do first? We have to get the ice cube up to its melting point. We're starting at -10, and remember the melting point of ice is 0. So we have to get it up to that 10 degrees. Since we are changing the temperature of ice, we are going to want to use our specific heat of ice, 2.09. By the way, if this is still the first day that you're watching this, you might want to stop, right? Because there are only 10 questions, and we're on question 4. Like I said, I recommend that you break this up into like 2 or 3 days. So maybe this should be the last one that you do. I don't know. Anyway, coming back to this, 300, no, not 300. What are we doing? We're heating ice. That's 2.09. 2.09 joules is the number of joules required to heat 1 gram of ice by 1 degree Celsius. I don't have 1 gram of ice. I got 45. And I'm not heating it by 1 degree Celsius. I'm heating it from -10 up to 0, right? Because I'm heating it all the way from here to there. I need to get it to its melting point. So the temperature change is 10 degrees. I'm increasing it by 10 degrees Celsius. All right, so now I need to think, what is the scale factor to get from the top quantity to the bottom quantity? Well, of course, I have to multiply by 45, and I have to multiply by 10. So that is multiplying by 450. So over here, I will multiply by 450. 2.09 times 450. I get 940.5. 940.5 joules. Sorry, I shouldn't have boxed that because it's not my final answer. It's just the answer for segment 1. Now for segment 2. By the way, have you noticed how I am labeling for every step individually? I'd really, 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 really appreciate it if you would do that too, especially on your test, because it makes your work so easy to follow. And you'll also like probably do better if you label your steps, because you're paying attention to what you're doing when. If you don't label your steps, it's easy to confuse yourself. It's easy to confuse me, and it's harder for me to grade. So if you want your grade back sooner, please organize your work nicely. All right, going into step 2 now. What are we doing? We're melting ice. If we are melting ice, then we need to use the heat of fusion. We know heat of fusion is 334. If you don't believe me, you can look at your own paper. 334 joules is the heat required to melt 1 gram of ice. I don't have 1 gram of ice. I have 45. So it's going to take 45 times as much energy. So 334 times 45. I get 15,030 joules. That is the energy required to do step 2. All right, to do step 3, what are we doing now? What state of matter are we in? We've just melted, so now we are liquid, and we are increasing the temperature. So if we increase the temperature of a liquid, that means we're going to use specific heat of water. Once again, our 4.18 joules per gram degree Celsius. So we can say 4.18 joules is the amount of energy required to raise 1 gram of water by 1 degree Celsius. I have 45 grams of water, not 1. And I am raising it from 0. Remember, we just melted, so we're at the melting point. We're going to heat it all the way up until its temperature is 50 degrees Celsius. So that is how much the temperature increases by. I need to figure out what that quantity is. So we're going to figure out what is the scale factor to get from our top quantity, to get from our top quantity to our bottom quantity. In order to do 1 times 1, turn it into 45 times 50, we have to multiply by 45, and we have to multiply by 50. So we'll do both of those together. That is a scale factor of 2250. multiplying by 2250. So that is the same number I will multiply my 4.18 by. I got now 9,405 joules. All right, step 1, 2, and 3 are all solved for. So now we can go ahead and add all these numbers up, and it should give us our total answer. All right, I got 25,375.5 joules. And yeah, looking good. All right, let's go on to question number 5. Engineers designing a cooling system that uses water. How much heat is released when 75 grams of liquid water cools from 80 degrees Celsius to 30 degrees Celsius? Oh goody, it's another one-stepper. I know it's a one-stepper because I stay in liquid the entire time. No phase changes are mentioned, and we're just changing the temperature. Yep. So cooling curve this time because we are cooling it down, so my temperature will decrease like that. Just a one-stepper. If we are cooling down water, once again, we're using our 4.18 number, right? Because we only use that when we're in the liquid state and we're changing temperature. Remember that 4.18 joules is the number of joules of energy it takes to cool down 1 gram of water by 1 degree Celsius. I'm sorry, I misspoke there. I should have said it is the amount of energy released when we cool down 1 gram of water by 1 degree Celsius. I don't have 1 gram here, I have 75, and I'm cooling from 80 down to 30, which is a change of 50. So that's how I'm going to figure out my scale factor there. To get from 1 by 1 to 75 by 50, I need to multiply by 75, and I need to multiply by 50. So I'll do them both together. 75 times 50, I get 3750. All right, so that's my scale factor. I'm going to use the same scale factor over here on the left, times 3750. 4.18 times 3750 gives me 15,675 joules. There's my answer. Question number 6. Science class is performing an experiment on condensation. A 36-gram sample of steam at 100 degrees Celsius is cooled and condensed into liquid water at 40 degrees Celsius. What is the total energy released? Okay, so we have another cooling curve. We can see, once again, we are at 100 degrees Celsius, and we're going to condense into a liquid. So we're already at the condensation point, or the boiling point, whatever you want to call it, of water. So we're free to just condense, and then we will eventually have to cool down to 40. Remember that we start at 100, and we're going to condense, 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 and then cool, 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 until we make it down to 40 degrees. So this is a two-stepper, right? First we condense, and then we cool liquid water. Condensation, so that means we're going to use our heat of vaporization number, which is, oh man, I forgot. What is it? 2257. 2257 joules is the amount of energy required to boil 1 gram of water, or we can say it's the amount of energy released when 1 gram of steam is condensed. I don't have 1 gram of steam. I have 36. So I need to scale this up by a factor of 36. It's just because it's been a while since I've said it. Remember that we don't need to put any temperature here at all because we're doing a phase change, so the temperature doesn't change. We don't need to account for temperature when the temperature isn't changing, right? That's what we care about, is temperature change. So we're staying at 100 degrees this entire time that we're condensing. So I just need to multiply my 2257 times 36. And when I do that, I get 81,252 joules. All right, so that's step 1. Next, we got step 2. Step 2, we are cooling down until we hit a temperature of 40. All right, and what state of matter are we in? We are in the liquid state, so we're going to use our 4.18 number once again. It's my favorite number, oh my god. Okay, 4.18 joules is the number of energy released when we cool down 1 gram of water by 1 degree Celsius. not doing 1 gram of water, we're doing 36, and we're not cooling down by 1 degree Celsius. We're cooling down from 100 down to 40, which is a temperature difference of 60. So to get my scale factor, I need to multiply by 36 and multiply by 60. So I'll take 36 times 60, gives me 2160. Is my scale factor here, and it must also be my scale factor over here, because it must take 2,160 times as much energy to do this if we are doing that. All right, so I'll go 2160 times 4.18. I get 9,028.8. Sure, yeah, whatever, I'll take that 0.8. There we go. So that is step 1 and step 2, both solved. Now we just got to add those numbers together. I got 90,280.8 joules. Very good. Okay, we're over halfway done. A researcher is measuring the energy needed to heat a solid. How much energy is needed to heat a 50-gram block of ice from negative 25°C to 5°C? Oh, look at that. It's a one-stepper. I know it's a one-stepper because we are staying in solid the whole time, so no phase changes. And all we're doing to that ice is changing the temperature of it, going from negative 25 up to 50. So this is going to be a real simple heating curve. Just goes up like that. And for our calculation, we need to use the specific heat of ice, because that's what we use when we change the temperature of ice. So we're going to use our 2.09 number. 2.09 joules is the amount of energy required to raise the temperature of 1 gram of ice by 1 degree Celsius. I don't have 1 gram of ice, I have 50 grams of ice, and I'm not heating it by 1 degree Celsius, but rather 20, going from negative 25 up to 5. That is a difference of 20 degrees Celsius. That's how much I am raising it by. Remember what this one means, right? It's not the temperature, it's how much you're changing the temperature by. So that's why this is a 20 and not a negative 5. It's also not a negative 25 or a negative 30 or anything crazy like that. It is the temperature change. We go up by 20, therefore there's a 20 there. All right, sorry, I'm getting a little loopy. We need to figure out the scale factor here. That is multiplying by 50 and multiplying by 20. So I'll do them both together. 50 times 20 is 1,000. So that means I need to multiply my 2.09 also by 1,000. So I got 2,090 joules. There we go, I'm done. That's the one-stepper. 3 more. Power plant technician is monitoring the boiling of water for steam generation. How much heat is required to convert 25 grams of liquid water into 50... What? Of liquid water at 50 degrees into steam at 100 degrees. All right. So here we do have a two-stepper. I know it's a two-stepper because I'm starting at 50, right, which is below the boiling point of water. And I'm going from liquid to steam. So there has to be a phase change in there and a temperature change. All right, so let's go my heating curve. Starting with liquid water at 50, heating up, and then we boil it, but it stays at 100. So we're going to boil it, and no increase necessary after that because it's going to stay at 100 the whole time, and then we call it. So two-stepper. First, we're heating up a liquid. So I'll use 4.18, that's the specific heat of water. 4.18 joules is the amount of energy required to heat 1 gram of water by 1 degree Celsius. How many times can I say that in one video? I don't have 1 gram, I have 25. And I'm not heating it by 1 degree, but how much? Well, I'm starting at 50. And if I'm starting at 50, what temperature do I go up to? It doesn't say, does it? Well, I know the boiling point of water is 100, don't I? So we're going from 50 up to 100. That is a temperature change of 50. Watch out. Don't put 100 there. That's silly. Put 50 because that is how much we are heating up our water by, right? We go from 50 up to 100. Okay. What's our scale factor here? $12.50. Same scale factor over here, 4.18 times 1250. I got 5,225 joules. Step 2. Whew. Okay, step 2. We are now boiling. I know I'm boiling because I am at a temperature plateau, right, which I've already decided that's happening. Temperature plateau boiling, so I'm going to use the heat of vaporization, which is 2257 joules, to do 1 gram of water into steam, right, to boil 1 gram of water. I don't have 1 gram of water, I have 25. So this is a scale factor of 25. Same scale factor on the other side, 2257 times 25. 56,425 joules. There we go. So step 1 requires 5,225. Step 2 requires 56,425. We add them together. I get 61,650 joules. And there we go. 2 more. Lab technician is condensing steam for an experiment. Calculate the energy released when 27 grams of steam condenses into liquid water at 100. Look at that, it's a one-stepper. I know it's a one-stepper because it only talks about condensing, and we're stuck at 100 degrees Celsius, which is the condensation point of steam, or the boiling point of water. So, just a one-stepper for us. Easy peasy. And it's also a phase change, so that makes our calculation even easier. The reason I say that is because we know that 2257, which is our heat of vaporization, the amount of energy released by 1 gram of steam condensing into liquid, we don't have to worry about temperature change. So this is actually really, really easy math. We are going from 1 gram to 27 grams, so it should release 27 times as much energy when we condense 27 times as much steam, yes? So all we got to do to get our answer is take our 2257, multiply by 27. $60,939 joules. I love one-steppers. Okay, question number 10. A sculptor needs to melt a block of ice for a project. Calculate the total heat needed to melt a 100-gram ice cube that is initially at negative 15 degrees Celsius. Okay, no one-stepper. Didn't get so lucky this time. This is a... How many steps is this? Wait a minute. Why does the sculptor need to melt a block of ice for a project? That doesn't make sense. Shouldn't he be freezing it for the project? Because if he's sculpting, you can't sculpt out of water. Silly sculptor. Anyway, sculptor is... So we're starting our ice at negative 15, and we need to melt it. So it can't melt at negative 15. If we apply heat to it, it won't start melting. It'll start increasing its temperature until it gets to its melting point, which of course is 0, and then it can melt. So this is a two-stepper. All right. Specific heat of ice, 2.09. Oops, sorry. 2.09 joules is the amount of energy required to take 1 gram of ice and raise its temperature by 1 degree Celsius. I don't have 1 gram of ice. The sculptor doesn't have 1 gram of ice. He has 100 grams of ice. That's also not very much for a project. Like, it's 100 milliliters. That's hardly anything. That's like an ice cube. Well, yeah, that's what it says. Sorry. It's going from negative 15 up to 0, so that is a temperature change of 15 degrees Celsius. What's my scale factor here? How do I get from 1 by 1 to 100 by 15? Well, I multiply by 100, and I multiply by 15, so I multiply by 1,500. 1,500. Same scale factor over here. 2.09 times 1,500. 3,135 joules. Step 2. What am I doing in step 2? I'm melting, aren't I? The sculptor is melting his ice for some reason. That seems counterintuitive to me. It's the opposite of what he should be doing. But he's melting his ice. I'm going to use heat of fusion then, which is 334 joules is the amount of energy required to melt 1 gram of ice. Our sculptor has 100 grams of ice, so that's going to be 100 times more energy. 100 times more energy than 334 is 33,400. All right, so I got 33,400 joules and 3,135 joules. Just got to add those numbers together. Here we go. I got 36,535 joules. Beautiful. All right. I hope that was helpful, because if not, I just wasted so many words. If you are still having problems with this, don't be afraid to come in for additional help. I will sit you down and we can go through more of these together. Yeah? So do that. All right. See you tomorrow.